Okay, we are looking at a new topic, a new section of the course called sequential logic. Now, in sequential logic, the basic building block is something called, basic building blocks are something called flip-flops. And with flip-flops, we then go on to build larger circuits. So let me show you some larger circuits. Now, flip-flops themselves are built using the very basic unit down to the core. There's something called an SR latch. S stands for set, R stands for reset, and there is something known as an SR latch, set, reset, latch. From there, we then do an extension. Okay. We then do an extension, and from the set, reset, latch, we come to the SR flip-flop. So let me just flip over to the camera. And I'm not going to do it over and over again, expecting that you, so this is the core basic block, the core block. You know, the most little piece of sequential logic, known as an SR latch. Now, by the way, I want you to note this. In this particular diagram, I have built the SR latch using two NAND gates. What are NAND gates? One type of universal gates. You can also build an SR latch using NOR gates. So please take note of that, all right? We can also build an SR latch using NOR gates. And the truth table will still come to be the same. This table here is only an analysis table. This table is an analysis table. Now from the SR latch, we did an extension. We introduced the clock line. So this is sometimes called a clocked SR flip-flop, all right? Or SR flip-flop for short. Then from the clocked SR flip-flop, we got again an analysis table or the truth table. We got an analysis table. From the analysis table, we got the flip-flop truth table, right? In the flip-flop truth table, we are basically looking at what is the state of the flip-flop. What bit is it storing in the next state given two inputs? All right? Okay. So then from the flip-flop truth table, we have the SR characteristic table. From the characteristic table, we come down to something known as the excitation table. Right? So these are all four tables. Now in the end, let me come back here. All right. So, okay. So that's all that we've been doing. Right. Now, I will show you something. There are four fundamental pieces four fundamental types of flip-flops. Now the first one I have demonstrated to you, the SR flip-flop. Yeah? So this here is all on the Moodle shell, right? This is a data sheet which is this here is a data sheet which is always given in every final exam. Right? This is given in every final exam. So this here is the 2018 final exam. So we start off with the SR flip-flop. So that's one down. Okay? SR flip-flop. The next flip-flop is the data flip-flop, D flip-flop. Then there is something known as the JK flip-flop. Then there's another one called the T flip-flop. So these are four fundamental types of flip-flops in sequential logic. And what I've done for you up till last week was we were covering the fundamentals of how our SR flip-flop works. So this here is the block diagram. This here is the block diagram of the SR flip-flop, right? So we package that up. If you look at the SR flip-flop, the circuit diagram, let me just flip over to the circuit. If we flip over, we find that the SR flip-flop has got how many inputs? 3 inputs, right? It's got 3 inputs and 2 outputs, Q and Q bar. What are the 3 inputs? Firstly, it's S, there's R, and the 2 outputs are Q and Q bar, right? This sitting inside here in red is the SR latch. Do you remember? That little piece in the red box is the SR latch. If we make another box, we will call that box the SR flip-flop box. So that's what this is, guys. So this data sheet, it's on the module shell. So if you look at this block here, this here is the SR flip-flop. The 2 inputs are S and R. That's our clock. Do you see this little triangle over there? That indicates there is a clock, right? Now, do you understand what this means over here? The little bubble. That means the clock is inverted, right? Okay, but the results will still be the same. Now, what table is this, guys? What table is this? Do you recall what table is that? That is the, so if you look at the table, let's have a good look. You've got your 2 inputs, S and R there, right? You've got Q, right? Q is another notation for Q is what? Qn, right? Q subscript n. And then on that side there, on the output side, you've got what? Q star. What is another notation for Q star? Qn plus 1 or Q plus, right? So what are we looking at? What table is this? We've done this table. I've shown you the derivation of this table. So all of last week I was showing you the derivation. I don't want to just see in engineering, it's important for you to understand how this basic building block works. I could have, if I wanted to, just showed you and said, hey, this is the table, use this table. But what I did last week in 3 lectures, it took a long time, right? I showed you piece by piece how we went from the latch to the flip-flop, from the flip-flop to the truth table, from the truth table to the characteristic table. This is the characteristic table. What does it have? You have the 2 inputs and your current state, and you determine what will be or you predict what will be the next state. Remember I gave you an example of the video game, or like a video game of sort, right? So that's the characteristic table. Now this here is the excitation table. You know your current state, you know your next state. What do you have to do to get from current to next, right? You know your current state, you know your next. What do you have to do to go from current to next state? So that's your excitation table. Now, what's this equation over here, guys? That equation, I derived it for you as well. We did the derivation. The derivation, we've done it. What is that equation? Where did that come from? That comes from, if you look at this table, the characteristic table, what are we doing? What is the purpose of the characteristic table? You have the current state. You know your current state, right? You know your 2 inputs into the circuit. You know your inputs. You know what is state. State means what's stored inside. By the way, guys, state means what is stored inside, whether it's storing a 0 or 1. By the way, I've asked this question before. How many bits does this flip-flop store? 1 bit, right? So it can either store a 0 or it can store a 1. All right? Okay, so this equation here, this Boolean expression here, is basically a rewrite of this table, right? So that table, if we put it into if we extract a Boolean expression using a Carnot map or whichever method you want, you will find that equation, right? Now, the last thing I want to show you is this. This here. That's what you call your state diagram. State diagram, okay? State diagram means what is stored, like what are the different options which can be stored inside your system. Remember, right now it's a 1 flip-flop system, right? We are referring to only this particular flip-flop. And how do you get from one state to another state? So this 1 flip-flop has only 2 possible states, 2 to the power of 1, right? It can either store a 0 or it can store a 1. So these are 2 circles are your 2 states. And basically these loops over here, they indicate how we can get from one state to the other. How can you make the 0 into a 1? How can you make a 1 into a 0? How can you, store and so forth. All right, now let me take you to the next one. So what I'm going to do, my plan is this. You see, SR flip-flop. When did we start on flip-flops, guys? Monday, did we start on lecture 1 of week 9? Or did we start on lecture 2? Okay, can we just roll back and check? Lecture 2, right? Okay, we started on lecture 2. So this SR flip-flop, yeah, week 9. I think I didn't put a date there. Yeah, I didn't put a date. Anyway, so that was all of week 9. So this here, we took all of week 9 to do all the proving for just one flip-flop. Now, I will very quickly show you the next flip-flop, D flip-flop. And we will use today's lecture in that. All right? Because D flip-flop, all flip-flops are related to each other. The thing about these lectures here is every little piece is related to the next piece. So for example, did you see how we built the SR latch? Then we had the SR truth table. Then using the SR latch and all that information, we had the analysis table, then the truth table. Then using all that information, we built the SR flip-flop. We went one step higher. Then we built the analysis table again. But for that analysis table, you needed the SR latch. Then we did the truth table. Then the characteristic table was based on the truth table. Then the excitation table was based on the characteristic table. Now, similarly, we'll move to the D flip-flop, and that's very similar as well, all right? Okay. Okay, because the idea is that by the end of this week, we will be able to apply it. Up till now, we are only learning the theory, right? Okay, then you may be asking then, what about these two, JK and T? Okay, for JK and T flip-flop, once you get the trend of what's happening, there's a video, my own video on the Moodle shell, which you can follow, but it's not, so long as you get the idea of how we went from a circuit which had a couple of NAND gates to how we came about with the truth table, from truth table to the characteristic table, from characteristic table to the excitation table, so long as you have a general picture. So that's why I'm going to show you with two step by step, every step along the way. So I'm going to take baby steps, I'm going to show you everything. Then we're going to move into analysis of systems. Okay, what does analysis mean? All right, let's show you analysis. Okay, analysis means you are given a circuit like this. Can you see there's two flip-flops over here, right? And you are required to find what is Y given the different values of X. That is analysis. You're required to find Y with now flip-flop sitting inside. This could have been an SR flip-flop as well, all right? I'm just saying analysis basically means you have a circuit given to you and you're required to find the behavior of that circuit. You're required to find the behavior, meaning what will the state of, during the first clock pulse, what will this JK store, what will that JK store, all right? Okay, because every flip-flop stores a bit. Either it stores a 0 or it stores a 1, right? And in the meantime, what is the Y? So that's what analysis deals with. Then I want to move to, very quickly, right? I want to move to something known as design. All right, so let's show you a design problem. This is a design problem. Design is the other way around, right? Design and analysis are opposites of each other. So what do we mean by this? Okay, so in analysis, a circuit is given to you and you're required to find the behavior. Okay, that what will be stored, what will be here, next clock pulse, what will happen, next clock pulse, what will happen, and so forth. That's analysis. To analyze the behavior. You're given something and you're required to work out how it will work or how it functions and so forth. Right? What happens when this is there, what happens when the input changes, what happens when the input is this, what happens when the clock is that. Right? Design is the other way around. Design is, I give you the behavior of a circuit. And design doesn't necessarily mean about sequential. Remember your problem when you did this particular midterm exam, right? By the way, I have to give you papers, right? So for your midterm exam, we will give the papers out this Friday. So for those of you who have not received the papers, if you could come to the Friday lab session in the morning, and we'll distribute it there then, okay? Turn up at about 9 a.m. in the morning, and we will distribute the papers there and then. But some students have already received. There's a handful of students still pending. Okay. Now, okay, what is design? Remember when you did your midterm exam, there was a question where you had to design a system where detecting an odd number system and a multiple of 3 or something along those lines. Yeah, so that's a design. The behavior of the circuit is given, the behavior of the system is given, and you have to build the circuit. So this is design. This is a design. This is a design a T flip-flop based circuit of sequential synchronous ring counter that goes through the following sequence: 2, 7, 4, 3, 6. Right? So that's a real problem. Right? Okay. So this could have been a system where you have traffic lights. Design a system whereby there's a red light, then there's a green light, then there's orange light, followed by red light again. Right? That's for one. But if you imagine if you have like a cross junction road, you have multiple traffic lights. So you have to consider all the possible scenarios. So we want to get to this. This is the end goal. Our end goal is to come to design. Right? Okay. Let's now continue our lecture. As I said, we have done from lock, stock and barrel absolutely everything. We have done absolutely everything with regards to the SR flip-flop. We now move to the D flip-flop, okay? We now move to the D flip-flop. So bring out your exercise books. All right, so today's date is 31st. All right. So you've got a D flip-flop. All right. Now, if you recall our circuit, let us package our SR flip-flop All right. So what I've done is I've packaged my earlier circuit over here into this. So that's how you will deal with it. When you do your labs and your projects and all that, you will deal with it. And by the way, guys, the reason why I'm heading more quickly towards design is because your project is in design. You will receive a design level project, okay? All right? Which will take about, it's like 2 labs worth of work. And I'll give you some extra time as well. Okay. So what we want to do is build a D flip-flop all right. Now, what we then do is tell me, what was one of the problems with our SR flip-flop? Have a look at this truth table. Have a look at that particular truth table. What can you tell me is one of the issues with our SR flip-flop? There is a problem in our design, and we recognize the problem in the design. Right? So the problem in our design is that when you have a 1-1, okay, luckily if you've got a clock of 0, no big deal, right? Okay, nothing happens. We're safe because SNR become obsolete. They become don't cares, right? If you've got a clock of 1 and SNR both equal 1, we have an invalid state. What does that actually mean? That means, what happens in that 1-1 situation? Do you remember the word I used last week? Racing, yes, racing. The flip-flop starts to race. It starts to blink on and off at a very fast rate, right? Okay, and that burns our flip-flop. So, so it's basically on and off means it's storing 1, then storing 0, storing 1, then storing 0. So what we're going to do is, we recognize that there is a problem over here. There is an invalid state. There is one scenario where that SR flip-flop doesn't work. So now, D flip-flop, in the D flip-flop, we want to fix that. We want to take it one step higher, and we'll say, hey, we're going to fix that. Okay, so how are we going to fix that? Right? Check this out. This is how. All right? Okay, let's do something over there. We've connected this new line called D. So what was S before is called D. And we now have we can package this up again. All right, now, okay, forget about the package. The package is only to make you realize that I've put it inside another box, right? So this is the, check this out. Inside the SR flip-flop, what is there? The SR latch. You add some more gates, what does it become? It becomes a SR flip-flop. From the SR flip-flop, you add one more gate. In fact, this NOT gate, is it possible we could have built it using a NAND gate? Yes. All right, so you can build this entire thing using NAND gate. All right, anyway, that's just a back-end story. The true story is this. Okay, you know this means jump, huh? All right, this means jump. The true story is this. If D is 0, what is S? 0. And what will R be? 1. If D is 1, because now there's only one input, right? If D is 1, what will S be? 1. And what will R be? 0. Okay. Any other possibilities, guys? Any other ways to shake this? Right? So the SR flip-flop truth table, right? And we want to extract the D flip-flop truth table from that. From SR, extract the D flip-flop. Okay, let's list our SR truth table. SR truth table, we had the clock. What else did we have, guys? Let's flip back. S and R. S, R, Qn plus 1. Sometimes people call this Q star, right? Okay, then we had, what else did we have, guys? Come on, help me out. You have 0xx 1 1 1 1 0 0 0 1 1 0 1 1, and then we say, hey, whenever it is 0, whenever the clock is 0 in this case, in our earlier case, right? I'm just rewriting, okay? I'm just copying. We said there will be Qn is equals to thing because it's in hold mode, right? Again, this will be Qn, which is hold mode, right? 0, 1, 0, 1, the Qn plus 1 was equal to 0. 1, 0, 1. And we said this guy was invalid. All right, now, have a look at this. This was our SR flip-flop, truth table, all right? This is the original truth table. We now realize that is this line 2 ever possible? Line 2, can S and R, look at this circuit. In the D flip-flop, can S and R ever have the same bits? No, absolutely not. Because if D is being fed, always R and S will be complement of each other. Alright? Will be complement of each other. So instantaneously we now know that for the D flip-flop, this line becomes cancelled out, or we can say, let's say that S is equal to D, right? S is equal to D, is that correct? Yeah, S is equal to D. Yeah. What about this line here, this last line? Gone. R, is there any R now in this new black box? No, R is gone. So that's what we've done. We've taken one flip-flop and we've modified it so that it works in a particular way. How many of you watched this movie, Toy Story? Right? And then there's Buzz Lightyear. And then what the guy does, I think in part 3, he goes and he changes the language setting of Buzz Lightyear. So he starts speaking Spanish. That's what we've done to the SR flip-flop. Right? So when he starts speaking Spanish, he becomes romantic. He's not aggressive anymore. So he doesn't want to fight against the bad guys. He just wants to be, you know, like a lover boy and all that sort of thing. So that's what it is. So what we've done with the SR flip-flop, it had a problem. There was an invalid state. So what did we do? We modified the circuit with just one simple adjustment and bang, finish. That invalid state is gone. Right? So now our D flip-flop truth table, so now our D flip-flop truth table will look something like this. We have a clock, we have D, any other inputs, guys? No more inputs. And we have Qn plus 1. Okay, clock. So let's now just, all we got to do is we got to copy paste from the top, right? Clock is 0, D is X. Well, if clock is 0, we already know this from our earlier learning, that if clock is 0, everything just switches off. So this becomes Qn, so we know this is in hold mode, right? If clock is 1, the two ones left, and D is 0, look at it over here, D is 0, right? Your Qn plus 1 is 0. If clock is 1 and D is 1, your Qn plus 1 is 1. Bang, done. What do you call this, guys? What do you call this? This will be called, right, set and reset. Right? But we don't use that word. So D is known as the data latch. So can you see it's a much neater, much nicer thing to do, right? Okay? Much neater, much smaller flip-flop. So that's the D flip-flop. So what was this over here? This was the SR flip-flop. We showed you what to cut out because we don't need the 1, 1, we don't need the 0, 0. It doesn't happen anymore. We don't need the R. There's no such thing as R anymore. It's sitting inside. So from the outside point of view, there's only a D and a clock and a Q in Q bar. Right? So there we go. That's our system. That's our truth table. All right. Now, next. From the truth table, so this is the new truth table. Now, let us take it one step further. What comes after the truth table, guys? The characteristic table. So D flip-flop characteristic table. All right, guys, do you remember? Guys and girls, sorry. Do you remember what is the characteristic table? You always must differentiate between the characteristic table and the excitation table. Characteristic table, you have your input. You know your D. What is your D? What is your SR? What is your JK? What is your T? Right? You know your input. Right? Okay, now, you also know your current state. You know what the flip-flop is storing. Is it storing a 1 or is it storing a 0? There's only two possibilities. Then, what are you going to do? You know your current input. You know your state. Then you're predicting your next output. What is the next state? Not output, the next state. Right? The output is the state. When we say output, output is the state. Excitation table. Excitation table, you know your current state, you know your next state, you don't know what your inputs are. You want to find out what should your inputs be in order to drive your circuit from current state to next state. All right? Okay. So let's draw that. So you have Qn, you have D, you have Qn plus 1. All right? So, guys, if you've got two inputs, what are the possibilities? 0, 0, 0, 1, 1, 0, 1, 1. Okay. Let's find out from our earlier table. Let's come here. Oh, right. D0, okay, and then Qn0. D0, D0. Let's look over here. That's our new table, guys. That is our new table. Okay? That is our new table. All right. D0. Hey, guys, what do you tell me about this? What can you say about the characteristic table? What's missing? Who's missing from the party? Right? Clock. There's no clock now. So we cover the clock up. D0, D0. Okay, D0 will give you a 0. Right? But D could have also been a 0 here. Yeah? D could have also been a 0 here. And it would have given what? The current state. So current state was 0. So in both cases 0. All right. Now let's look at 0, 1. D1. Eh? D1. All right. D1. Okay. So we have a D of 1. Right? Whenever D is 1, you get an output of 1. So in fact, you don't even have to refer to this line here, guys. You just refer to these two lines. Right? Again, D0, output is 0. D is 1, output is 1. What can you tell me is the relationship now of Qn plus 1 in terms of, if you look at the truth table, well, without even drawing the Carnot map, I know in the last round we did a Carnot map, without even drawing the Carnot map, what can you tell me about Qn plus 1 as an equation? Yes. So Qn plus 1, which is also sometimes called Q star, which is also sometimes called Q plus, is equal to D. All right? Okay, let's go to the, so that's our characteristic table, very simple and straightforward, right? No two ways about it. Let's now look at our, after characteristic table, what is the next one? It's the D flip-flop excitation table. In the excitation table, you always have Qn. You always have Qn plus 1. You have your current state and your next state. But you want to go backwards and you want to find what is your D. All right? So, if there's two inputs, how many possible combinations? 4 possible combinations. All right. Now, so always your excitation table, you refer to the characteristic table. 0, 0, let's look for where 0, 0 was. D was 0. 0, 1, let's go up. 0, 1, 0, 1, there. D was 1. 1, 0, let's go up. 1, 0, 1, 0, 1, 0, oh, it's here. 1, 0, D was 1, 1, 1, 1. Let's go 1, 1, oh, this last line. D was 1. Done. That's it. Okay? All right. So, I want you to notice how this was done. We had a SR latch inside the box. We put it inside a box. Then we connected some NAND gates. We made it into SR flip-flop. From SR flip-flop, you got analysis table, truth table, characteristic table, excitation table. Then we put in one more thing to correct that 1, 1, the invalid state. We made a D flip-flop. All right. So in the end, you now are equipped with, if you look at our data sheet, and by the way, this data sheet will be given to you in the exams. Oh, the other thing I wanted to mention is, please make sure that we have, that you attend the lectures. You guys are okay. Try and encourage your friends to attend, because we will be having a quiz every week, a small quiz. Maybe I might give you one of the truth tables or characteristic tables, something along those lines, but something small, 10 minutes, right? Okay, just to encourage your attendance. And by the end, you will have a test 2, but your test 2 might only be 1%, because all the rest of it will come from all the quizzes, right? Okay. We don't have much time. We have got week 10, week 11, week 12, week 13, 4 weeks to go. All right. Like one particular problem I was looking at for your final exam was to design a machine which plays rock, paper, scissors, right? And you can, do you know rock, paper, scissors? Right? Yeah, okay. But that you can use sequential logic to build that type of machine. Right? So, yep. Okay. Now, after we've done this, so let me just mention some chip numbers, guys. So your do you remember week 7 you built in your tutorial, you built a 7-segment display, and I think week 8 when you came back you built a 7-segment display in your lab, last week's lab, right? Okay, you built it using all the NAND gate and NAND gate, but there is a ready-made chip that's called the 74LS47 which will do that job, BCD to 7-segment converter or decoder. Now the D flip-flop is the 7474, also known as the 74LS74. So you will, as you go through this course, you will start to become familiar with many different chips. Like for example, what is the 74LS00? By now you should have used it so many times. It's a NAND gate. Then you have 74LS02, 74LS04, 06, 08. Okay, 7447 is the BCD to 7-segment display. What is the 74LS138? Anyone remember that? 74LS138, 328 decoder, right? 328 decoder, right? 74LS156 is your multiplexer, I believe, right? So similarly, your D flip-flop, it comes in a ready-made chip. Your SR flip-flop, if you are lucky, you'll be able to find the chip. I'm not sure, but generally, traditionally, SR flip-flop is not given as a ready-made chip. You have to build it using NAND gates. You have to actually build it using a bunch of NAND gates. So how many flip-flops do you need to build an SR flip-flop? How many NAND gates do you need to build an SR flip-flop? 4. And if you were using the 74LS00, how many chips would you need? 1 chip. Right? So this thing should now start to show to you. So your D flip-flop, you don't need to build it. If you want, you can, but you can use the ready-made chip, 74LS74. All right. Leading edge, lagging edge. All right. I want to show you Right. Now, for the purpose of proving, guys, what I've done is I've showed you each and everything about the D flip-flop. I've showed you each and everything about the SR flip-flop. We will now put on pause the JK and the T. All right? We'll put on pause on the JK and the T. It'll take me 1 week to show you JK. It's a very large flip-flop. But the important thing is you know the behavior. Right? In fact, there's many other flip-flops, but I have shown you the in and out of 2 flip-flops. The JK and the T, they work in the same manner. The important part is this. You should know how to use the characteristic table and how to use the excitation table. Okay? When to use the characteristic table, when to use the excitation table. What is the clock line? What is Q? What is Q bar? All that sort of thing. Q bar will always be the complement of Q. And JK is just like input. So JK, you could say, is another variant of SR. Just like D is a variant of SR, JK is also a variant of SR. Okay? T is a variant of JK. So it's like SR, from SR, there's 2 paths. You can build a D or you can build a JK. Once you build a JK, you can further modify JK to get a T. So they're all related. They're all from the same core. And they all work in a similar manner. Okay, now the important thing, I want to show you analysis before we finish off for today. So this is a circuit. Let's start off on a new topic. If you could write that down, analysis of sequential systems. I don't want to draw a full circuit, I just want to show you how this works. Analysis of sequential systems. All right, and maybe on the top just say we will use the JK and the T tables and so forth. Only the proving I haven't showed to you because it takes a long time. And this year we've got a shorter semester. All right. Now, firstly, everybody have a look at the board, have a look at the screen. Now, I want you to advise me. First question to you: how many flip-flops are there? How many flip-flops are there in this system? How many flip-flops will be used? 2. So tell me, this system, as a system, how many bit system is it? At any point in time, how many bits is it storing? How many bits is it handling? 2 bit. Where do we get the 2 bits from? Because there's 2 flip-flops, so it will be a 2 bit. Every flip-flop, 1 bit. Right? 1 bit per flip-flop. Okay? Alright, now, you've got a clock line. Now, I want to introduce a new word to you. The word is synchronous. Right? Synchronous. Right? If you want to note it down, you can note it down. It's a very simple word. Synchronous. Synchronous means, well, what does synchronous mean? When somebody says, let's synchronize our watches. It's in sync, right? Everybody is moving together, right? If anything is synchronized, that means people are moving together or machines are moving together. Now, in this particular case, your 2 flip-flops are synchronized. So that means your clock pulse, right? Can you see this clock pulse? It is connected to the same clock pulse is connected to both flip-flops. So the flip-flops are flipping together, right? Okay, what is the purpose of the flip-flop? What is the purpose of the clock? The purpose of the clock, we've introduced the clock before, right? The clock is the signal into the flip-flop which says, okay, read. It's like the read signal, right? When you send a clock pulse, depending on whether you've got a bubble or a no bubble, right? If there's no bubble, it will work in leading edge. If there's a bubble, it will work in falling edge. And I'll explain what leading edge and falling edge means. Now, what it means is, if you have a system, right? Let's go up. Okay. What the clock means is, at what point in time do we tell the flip-flop to now read? Otherwise it will be continually reading. So what it does is, it's like you pressing the memory button. When you press the clock button, right, when the clock signal changes, right, depending on whether you've got a bubble or not, right, okay, whether you've got a bubble or not, it will determine how your flip, or what to take in. Otherwise, you could have a number of things going into your D, right? It could be floating up and down, right? But the clock is the line which says, yes, now read, now read, now read, now read, take action, take action, take action. Right? So the clock is one of the principal controllers. Now, the other two words I want you to note. There's something called leading edge, right? Leading edge is when the clock pulse goes from a low to a high. Sometimes they call it a rising edge. Rising edge. R-I-S-I-N-G, rising edge. Trailing edge is when the clock pulse goes from a high to a low. Right? Obviously, there's only two things. Either the clock pulse can go from a high to a low, low to a high, or it can go from a high to a low. So this particular flip-flop will only function when the clock pulse goes from high to a low. And this one here will go from low to a high. Then it will take in what is D. All right? Okay. Let's now come back to our particular picture over here. All right. Okay. There are two flip-flops. That means it's a 2-bit system. How many inputs, apart from the 2-bit system, how many inputs into the system? I'm not talking about the flip-flops. How many inputs into the system? One input. Can you see there's one input? One input. How many outputs in the system? One output, Z. Right? Input is X, output is Z. In the meantime, apart from the output, how many states are there? Right? States. Right? States means the system, what memory is it storing in the meantime? It's 2 states. 2 flip-flops, every flip-flop has a state, which is, state basically means, state means what bit is it storing? What bit is it storing? Is it storing a 0 or 1? So because there's 2 flip-flops, so there's 2 states. There are 2 pieces of memory. Right? Okay, so we have one input, which is X, one output, which is Z, 2 states, flip-flop 1, flip-flop 2, and a clock line which is synchronized. Now, I want you to give me the equation for D1. Have a look at this diagram. What is the equation for D1? What is the equation for D1? Okay, D1. All right. Forget about this thing here. We label this as D, right? Label that output as D. Set. Okay. What is coming into this AND gate? Firstly, let's look at this AND gate. What is coming into this AND gate? Okay, X, and Q1 bar. So what will we write over here? X and Q1 bar. Okay, about this one. Let's think about this one. What's that, guys? That's Q1 and Z. Q1 and Z. Right? So over here we write Q1 and Z. Over here we write X and Q1 bar. Okay, let me. So we have Can you tell me the 4 inputs, guys? What was this? This was X. This was Q1 bar. This was Z. This one was? Have a look. Second line was Z. The other one was Q1. Okay, Q1.